Okay, so this video we're going to look at mainly two things. We're going to quickly review Bronsted-Lowry, then we're going to talk about positions for equilibrium, and then we're going to get into buffers. So we've talked about Bronsted-Lowry acids and bases throughout this unit, right? So hopefully by now you can recognize that the acid is the substance that's going to donate the proton, and the base is the substance that is going to accept that proton. So we always find that it's an acid plus a base when we are looking at these Bronsted-Lowry equilibrium reactions. So a couple of old diploma questions, just to kind of give you a feel for what this is going to look like. So it says the following equilibrium system maintains a constant pH in the intracellular fluid in the body. So a Bronsted-Lowry acid in the equilibrium system represented by the equation above is blank, and it will blank the Bronsted-Lowry base. So when we're looking at this, right, we've talked about conjugate pairs, right? So we have the H2PO4 minus, which would be paired with the HPO4 minus, right? So that would be one of our pairs. And our other pair would be the water with the hydronium, right? Because remember the difference for conjugate pairs is one has the H and one doesn't. So Bronsted-Lowry acid, so when I look at these, when I look at what's happening, I can see that H2PO4 minus is turning to HPO4 minus. So it is losing a proton. When I look at the water, it's turning into hydronium, so it is gaining a proton. So by definition, the Bronsted-Lowry acid is what loses the proton. So it's not A and it's not B, we're left with C and D. And it will blank the Bronsted-Lowry base. So acids are going to donate protons to the base. So we are looking at C for that one. Okay, here's another one. So a solution containing the ammonium ion is mixed with a solution containing the hydrogen carbonate ion. So in the forward reaction, the Bronsted-Lowry base is blank and its conjugate acid is blank. Okay, so to be able to answer a question like this, what we want to start by doing is figure out what our reactants are going to be. And we already know what they are because the question tells us that we are reacting ammonium with a hydrogen carbonate. So what we're now going to do is we're going to go to our data table. And the reason we're going to go to our data table is we need to figure out what is what, right? We need to figure out what is going to be the acid and what is going to be the base. So when we look at our data table, right, we're looking for the hydrogen carbonate and we are looking for ammonia. So hydrogen carbonate can be found here in the base column. It can also be found down here in the acid column. Then we have ammonium. So ammonium is here in the acid column. So we have to have an acid plus a base. What we're going to find is when we look at this data table, and this is something that we haven't talked about yet, but we're going to talk about in this lesson, is the fact that all of these acids and bases are in a particular order in this data table. They're not just randomly placed into here. Right, so if you look at our Kas over on the right-hand side, you should notice that they're getting smaller and smaller. So what that's actually telling us, or is giving us information for, is how strong or weak our acids and bases are going to be. So when we are looking at our acids, right, they're in this column. You know by now you have your 6 strong acids up here, and that everything below the gradient area is going to be weak. Okay, what we find is that out of all of these weak acids, they're in order. So oxalic acid, being the first one under the grayed out area, is the strongest of the weak acids. And as we go further down the table, they become weaker and weaker. So that means all the way down here at the bottom, the hydrogen phosphate ion, that's our weakest acid that we find on the table, okay? And our bases, they go in this column. So if you think about how we figure out KBs, we did KW divided by Ka. So what you actually find is that the phosphate down here, out of all of these weak bases, has the largest Kb. So this is actually going to be our strongest of the weak bases. And as we go up the table in the base column, they're going to get weaker and weaker. Okay, so that means our weakest weak base is going to be this HOOCCOO minus, right? We've already talked about how these 6 up here in the conjugate base category are not actually conjugate bases because they don't have the ability to reverse, right? These are strong acids. We use single-headed arrows. So it's important to recognize that for our acids, when we're talking about weak ones, this is the strongest weak one, and the further down we go, the weaker they become. And for bases, down here at the phosphate, that is our strongest one. And then they get weaker as we go up. Okay, so why that matters. So for this equation, we've identified that we have ammonium. Ammonium can only be an acid. So we kind of already know that it has to be an acid. We have the hydrogen carbonate ion, which we found in both of the columns. So it's amphiprotic. It could be an acid or it could be a base. So in this case, the ammonium is going to be my acid and the hydrogen carbonate is going to be my base. So part of why that's going to happen, one, ammonium can only be an acid. So it doesn't have the option to be the other. The other reason it's going to be the acid is you're going to find that it's always going to be the strongest of the weak acids that's going to be the acid, and the strongest of the weak bases that is going to be the base. So if I were to mix a whole bunch of them together, I would want to go to my data table and kind of figure out what is what, okay? So in this case, the ammonium, excuse me, is going to be my acid, and the hydrogen carbonate is going to be my base. So now, if we go back to here, we can figure out what this is going to turn into, right? So if we're saying the ammonium is going to be the acid, it's going to lose a proton, so it's going to turn into ammonia. Okay, because we said the hydrogen carbonate is going to be the base, it's going to gain a proton, and it's going to turn into this carbonic acid. Okay, so now we can actually answer the question. So it said in the forward reaction, the Bronsted-Lowry base is, well, we've already established that the base is the hydrogen carbonate ion, right? Because ammonium can only be an acid. Okay, so its conjugate acid is, so the conjugate to HCO3 minus is going to be the H2CO3, right? Because the only difference between them is this has 2 H's and this has 1, so it has the extra. So we're looking at A for our answer. Okay, so next type of question that you see on the diploma, which is quite common, has to do with positions for our equilibrium reactions. So in these questions, they're generally going to give you an acid plus a base, and it's not going to be like something in water. It's going to be 2 things that are in that acid-base data table. And then they're going to ask you which direction is favored at equilibrium. So what I need to do to figure that out is basically identify my acids and my bases. Once I figure out what the acid is on the right side of the equation, I'm going to figure out what the acid is on the left side of my equation. I'm then going to go to that data table, and I'm going to figure out of those 2 acids, which one is stronger. Okay, whichever one is stronger is going to actually act as the acid, right? So if I have, think about a general equation, we have an acid plus a base, and that's in equilibrium with their conjugates, right? So we're going to have another acid and base on this side. So it tends to be easiest to figure out what is this acid, what is this acid. Go to the data table, figure out which one is stronger, and the stronger one's going to be the one that's higher up in the table. If I decide that this one is stronger, so if I'm choosing this one as the stronger acid, so I'm just going to, oh, that's horrible, I'm trying to write SA for stronger acid, then it's going to shift this way. Well, I shouldn't say shift, that's not the right word. The equilibrium position will lie towards the right because this is the stronger acid and it wants to behave as the acid. If, on the other hand, though, I find that this one is actually the stronger acid, then I'm going to find that it wants to behave as the acid, and the equilibrium position is going to lie towards the left. Okay, you will find the diploma sometimes will ask you like which equation, and it'll give you 4 equations going to favor reactants, or which equation is going to favor products. But one of the newer ways that they've started to do that is they're going to give you an equation, and obviously it'll be a real equation. It's not going to say acid plus base, it's going to say something else. And then it's going to give you your equilibrium arrows. And you're going to see that over those arrows, it's either going to say greater than 50%, or it's going to say less than 50%. Okay, I remember the very first time I saw that, I was kind of like, what is going on? And I thought about it for a little while, and then I realized what it was getting at. So when it says greater than 50%, that means that this reaction proceeds towards products more than 50%. So that's basically telling me that products are favored, and I have more products at equilibrium. If it says less than 50%, this means I have more reactants than I have products, so it is going to be a reactants favored. I know there's an example here, but there's a bunch of like diploma examples, so we'll just look at those instead to kind of give you a feel for this. So here we have our equation. So it says which of the following rows identifies the stronger acid and the side of the equilibrium that is favored. So first thing I want to do is figure out what are my acids in this equation, right? So these are my reactants. So out of the two, this is the one that's going to be the acid, right? It has the H. This has no H, so it can't be the acid. Over on this side, this is the one that is going to be my acid, right? Part of the way you can also figure that out is there's the one conjugate pair. Here's your other conjugate pair, right? We know that within each pair, we need an acid and a base. So now that we've identified what the two acids are, we need to go to our data table to figure out which one is stronger. So we have HNO2 and C2H5. So we're going to start at the top. Okay, here's HNO2, and here's the C2H5O. So that means out of the two, because the HNO2 is higher in the table, the HNO2 is going to be the stronger acid. Okay, so this is going to be the stronger acid. So it's not C and it's not B. So the side of the equilibrium that is favored, because the HNO2 is the stronger acid, equilibrium position is going to favor those reactants. Okay, here's another question. I'll let you guys work through this one, but same idea. You should be able to see, always check your KAs when they give you a question like this. Make sure that they're actually in the appropriate order, because sometimes they are not in the appropriate order. In this case, they are, and I know that they are just by looking at the values of K. They're going from the bigger K to the smaller K. So I know that this is the strongest one and this is the weakest one. So same idea, this one's asking you which one favors products. So for it to favor products, I need to have my stronger acid over on the reactant side. So a couple of different ways to approach it. One of the ways is just to be like, okay, well, this is my strongest acid of C2H3ClO2. So if that's on the reactant side of any of these, then I know that's going to favor products. But it's not. So we go to our next strongest, which is C7H6O3, which is in here and here, right? So we're looking at this one and this one. So for it to favor it, we need to have it paired with something that is weaker. So we look over on this side. Okay, so these were the acids on this side. When I look over on this side, the acid is going to be this one and this one. So C2H3ClO2, that was the strongest acid, so that would actually favor the reverse direction. But when I check here, the C3H6O3, that's down here in my table, right? So we'd be comparing this one with this one, because this one here is stronger. That's why we're going to choose B as our answer. Okay, so a bunch more questions, kind of all following the same idea. I'll let you guys practice those ones on your own. Same here, this is just basically ordering things. So finding things in your data table, figuring out where they belong. We're just going to skip through all of these, and you guys can definitely use these as practice problems to help you study for some stuff. I think I also just have some like random KB ones thrown in here because I think I didn't put them at the end of the KB lesson. But yeah, good practice for you to practice through those diploma questions. If you log on to D2L, I'm quite sure all the answers for those are posted in the notes part, okay? So now we're going to get into the second half of the lesson, and we are going to talk about buffers. Okay, so hold on. Okay, so when we talk about buffers, buffers are basically defined as a solution that are going to resist changes in pH. So what that means is when I add either acid or base to it, I'm going to find that the pH of that solution doesn't really change. So this is different than water, right? If I take water and I add some acid to it, I'm going to notice that the pH changes significantly towards the acidic end. And if I take water and add base, I'm going to find that it's going to change significantly towards the basic end. So what we find is that with buffers, these are solutions that when we start to add acid and base, they don't really change with respect to the pH. So, oh, hold on, didn't need to do that. I have to move this. So, if you think about titration curves, remember when we talked about weak ones, we said there was always going to be that little dip at the beginning. So why we find we get that dip is we start with whatever our weak acid is. And originally, there's very little of its conjugate in solution because weak acids don't go very far towards completion. But what happens is as I start to add base to it, I start to create more and more of the conjugate. And then eventually I reach a point where I have enough of the conjugate that I create what's known as a buffer. And we see that even though we're adding base to it, the pH isn't really changing significantly. Okay, eventually we reach a point where it does, right? And that's where we start to see that we go in towards that equivalence point, we get that straight vertical section. And that's because we've exceeded that buffering capacity. So what we find is that at the middle of the buffer region, which is right here, right? Because this is kind of in the middle of where it's resisting changes. We find that the concentration of the weak acid, so we can say HA, is equivalent to the concentration of the A- or its conjugate base, okay? So why this creates a buffer and why this is going to resist changes in pH. If you think about some of our equations, right? So let's say we have HA capital combining with water, right? Because we do have water in here. This is going to set up an equilibrium with the A- and hydronium. So, why is this solution going to resist changes in pH? Well, it all comes down to Le Chatelier's principle, right? Remember we talked about Le Chatelier's principle, one of the things we talked about was changes in concentration. So if we add acid to this particular system, we would be increasing the hydronium concentration. This system would be able to resist that by shifting away from it. If we were to add base, it's going to be able to resist that because even though hydroxide isn't in this equation, remember that hydroxide can react with hydronium to neutralize and form water. So by adding base, I reduce the amount of hydronium, and this shifts to the right to replace the hydronium, or to try to replace the hydronium. And again, we see that we don't really have a large change to the concentration of the hydronium, which is why our pH is going to stay somewhat stable. Okay, still definitely going to change, right? When you look at the curve, it does change. It just doesn't change significantly, right? So it's able to try to resist those changes that we have. So buffer is going to be able to resist it because it has to have a reasonable concentration of A- and HA. Right? If I have a lot of HA but very little A-, sure, I could shift to the right, but I'm not going to be able to shift very much to the left because I'm not going to have enough A-, right? And that's why initially, as this sets up, it does change the pH because I don't have enough A-. But as I start to create more and more A-, as I neutralize the HA, then what happens is I'm able to establish this equilibrium system where I have a pretty decent amount of HA and also a decent amount of A-, which means I can shift to the right or I can shift to the left, depending upon what I do to that hydronium and hydroxide concentration, okay? So, 2 ways to make a buffer. So if you think about what we need to have a buffer, right? We said we need to have our HA along with its A-. Okay, buffers do also exist for bases, okay? We would just need the weak base and its conjugate acid, okay? So what we find is there's kind of 2 ways to be able to create a buffer. One way is kind of like in that titration curve that we just looked at. So if I add a strong base to a weak acid, that is going to form the conjugate base to that weak acid, and then I'm going to be able to establish a buffer. The other way that I can do it, which tends to probably be the more common way of doing it, is to basically add equal molar amounts of the weak acid and the conjugate base in the form of an ionic compound to a solution, right? So if I were to add, let's say vinegar, because vinegar, CH3COH, is a weak acid, and I were to add sodium acetate, right? It contains the acetate ion, which is conjugate to acetic acid. And that's one way that I could do it, okay? So always going to be questions on buffers on the diploma, always. So make sure that you star this and you look it over, because I guarantee you there'll be a question. There's always 1, sometimes 2 questions on it. And I'll show you in a little bit some examples of what they're going to look like. So how do buffers work? Well, we kind of already talked about this in the last one, or not the last one, but in one of the earlier slides, right? So we said that they're going to have a weak acid or base along with its conjugate pair, and they're going to set up an equilibrium solution. So when you start to add acid or base to it, it's going to neutralize that water, or it's going to increase the hydronium or the hydroxide, depending on what you have, okay? So here's an example of one equation, right? So normally you're going to find that this equation would be written the other way. I'm not really sure why I have it written this way. Can I even move it? It doesn't really matter that it's written this way, but what I mean by that is normally for a buffer, we're always going to have whatever our species is plus water. The only time we're really going to say that it's reacting with hydronium or that it's reacting with hydroxide would be if I told you you have an acetic acid, an acetate ion buffer solution, and you add hydronium to it. Then you could write the equation this way. But generally, you're going to find that this equation would be written the other way. So it'd be this plus water to give us this, right? So if we add a base to this buffer, the hydroxide ions are going to react with the hydronium ions in the solution to make water. So by adding base, we're going to decrease the concentration of the hydronium. So because we decrease the concentration of the hydronium, it is going to shift. I don't know why it's saying right. That should say left. It probably says right because the equation was meant to be written the other way. And obviously I didn't write it the other way, so sorry. But yeah, if you could change that down here so that it does say left, right? And that's because by adding hydroxide, we're going to react with hydronium, which is going to lower the concentration of hydronium. The system is going to want to shift to the left to be able to increase the concentration of the hydronium. So there are some characteristics of a buffer solution. So what you'll find is different buffers are going to have different pHs at which they operate. Why they have different pHs? It's going to depend on, did you use a weak acid to set up the buffer? Did you use a weak base to set up the buffer, right? So if I were to use, let's say vinegar, which I keep talking about as a buffer, that's going to have a pH around 2.6. Whereas if I used ammonia to set up the buffer, I'm going to find that that's going to have a pH closer to like 8 or 9 kind of thing. So what you'll find is the pH is going to differ based off of the strength of the particular acid that you have. So buffer capacity basically refers to how much acid or base, sorry, this says bugger, and I have no clue why. It's probably auto-corrected buffer to bugger. Okay, so buffer capacity is going to depend on how much of the acid and conjugate base or base and conjugate acid you have present in your solution. The higher the concentrations are, the greater the buffering capacity is going to be. Okay, if you don't have very high concentrations, you're going to find it's going to have a pretty low buffering capacity. And that's because if I don't have a lot of it, it's not going to be able to shift far this way or this way, at which point it's going to have a minimal buffering capacity. Okay, so generally when we talk about buffering capacity, that's basically referring to when we exceed the point where it has the capability to resist those changes in pH. So where we see that when we start to add stuff, the pH starts to change significantly, then I know that I've exceeded the buffering capacity because it's not able to counteract that change anymore. Okay, you're never going to be asked to calculate when that's going to happen. We don't really worry about that in Chem 30. You're going to see that you are going to deal with that in first year Chem next year, but we don't really talk about that in Chem 30. So just recognize that what we're trying to get at is buffers only work for so long, and then they're not going to be able to counteract that change anymore. So it's not like I can add an infinite amount of acid or I can add an infinite amount of base. Eventually I'll reach a point where it's not going to buffer it anymore, and I'm going to see that the pH is going to change. So you have buffers in your bloodstream. Right? Sometimes we don't really think about it. Some of you who have taken bio think this is more bio 30 than bio 20, but honestly can't remember. You should be aware of the fact that you have buffers in your bloodstream. Okay, so your body has to maintain a pH in your bloodstream between 7 and 7.5. If you go outside of that range, that can definitely be life-threatening, and you could die from it. So obviously we don't just drop dead every 2 seconds. So there must be something in our bloodstream that's able to ensure that we stay within that range. So your bloodstream actually has a couple of different buffer systems in it that are going to resist those changes. But probably the most common one, and I don't know why this looks so wonky right here. Do I have like a picture over a picture? Yeah, there we go. Has to do with carbonic acid. So why carbonic acid? Well, obviously your cells are constantly creating carbon dioxide, right? We take oxygen in, we put carbon dioxide out. Carbon dioxide gets taken away in our bloodstream. When the carbon dioxide goes into the bloodstream, it undergoes a formation reaction with water to form carbonic acid. Carbonic acid has the ability to set up a buffering system because it's a weak acid, right? So that carbonic acid can combine with the water to produce hydronium and hydrogen carbonate ions. What we find then is as our body produces acid or base, this buffer system is going to be able to shift. The other advantage to this particular one is that HCO3- can also undergo an additional step to be able to buffer. Okay, another one you have in your bloodstream is the phosphate ion, right? And that also has 3 steps to it. But recognize that you have buffers in your bloodstream that are going to prevent significant changes in pH. And that's what's going to allow for your body to maintain that pH between 7 and 7.5. Okay, so let's look at some old diploma question. So the following equilibrium system maintains a constant pH in the intracellular fluid in the body. Okay, this is important that it says a constant pH. When it tells you that something has a constant pH or that it resists changes in pH, it's basically telling you that it's a buffer, but you have to be able to recognize that that means that it's a buffer. Okay, so terms associated with acid-base equilibrium systems. We have buffer, we have amphiprotic, polyprotic acid, polyprotic base, and a conjugate acid-base pair. So it says which of the terms numbered above can be used to describe the reaction or the species in the equilibrium system above. Okay, so term 1, buffer. Yes, this is a buffer, right? The question told us it resists changes in pH. Amphiprotic. H2PO4 minus has a negative and an H. So does the HPO4 2 minus, so it is amphiprotic. Okay, polyprotic acid. Well, here's an acid. It has two H's. So yes, we have a polyprotic acid. Polyprotic base. So what are our bases? Our bases are going to be water and HPO4 2 minus. This has a 2 negative charge. That 2 negative means it has the ability to accept 2 protons. So yes, this is a polyprotic base. And then a conjugate acid-base pair, absolutely we have conjugate pairs because we have an equilibrium system. So we are looking at D. 1, 2, 3, 4, and 5 are all true for this particular equation. Okay, this question here, put like a star or something in your notes. This question shows up so commonly on the diploma to the point that sometimes they don't even change the chemicals in it, okay? So if each pair of solutions listed above is mixed together in equal amounts, then the pair of solutions that would act as a buffer is. So if you think about what's going to act as a buffer, we need to have something weak in solution with its conjugate. So for one, we have hydrochloric acid and sodium hydroxide. This is a strong acid and a strong base. So that's a negative. It's not going to be a buffer. Okay, then we have HClO4 and KClO4. So we do have conjugates because we have the HClO4 and the ClO4 minus, but HClO4 is strong. So that's also not a possibility. Okay, then we have sulfuric acid and lithium hydrogen sulfate. We have the exact same problem here as we did in number 2. Sulfuric acid is strong, so it is out of the mix. Okay, for solution 4, we have phosphoric acid, so that's a weak acid with sodium dihydrogen phosphate. So this has the ability to be a buffer. We have conjugate pairs, right? Because here's H3PO4, here's H2PO4, and they are weak. So the one that could act as a buffer is going to be D. Okay, so here's another one, slightly different version, but the same idea. So the two species listed above that could be combined to prepare a buffer solution are. So we need to find things that are conjugates, and we need to find things that are weak. So when we look here, water and hydroxide, they're conjugate, but they're not going to make a buffer. OCl minus, we don't have an HOCl, so that's not going to work. This guy here, we don't have either an H2C6O8, what am I saying? H2C6H6O6, and we also don't have a C6H6O6 2 minus. So this is missing a conjugate. But these two here are conjugates of each other, right? This has the H, this doesn't. So 5 and 6 have the ability to form a buffer. Okay, so here's another one, pairs of solution. If each pair of solutions listed above is mixed together in equal volumes, then the one that could act as a buffer is. So this is the identical question to, not that one, that one. The only difference, they gave us some concentrations in here, right? But same idea, we're gonna get all the way down to option 4 for the same reason. These are not conjugates. These are conjugates, but they are strong, so they're out of the mix. So we are looking at D for our answer, okay? So that's going to be buffers. Buffers tends to be something that you guys do struggle with. So really important to make sure that you work through the buffer stuff that's in your booklet. Biggest thing to recognize with buffers, they're going to resist changes in pH. We have something that's weak in solution with its conjugate. It's going to be a Le Chatelier system. It's going to be able to shift, which is why it resists those changes in pH, okay? They definitely, of late, on the diploma, have really been kind of harping more so on recognizing buffer systems from your pH titration curves. So really important to make sure that you're able to recognize where the buffer is on the curve. So it's always right after the dip, okay? And it's only for your weak species, not your strong species. Important to be able to recognize that that's where the concentration of the weak acid and its conjugate base are going to be approximately equal. Or if you're dealing with a buffer where you started with the weak base, it's going to be where the weak base and its conjugate acid concentrations are going to be approximately equal, okay?